next talk is entitled FireComb Network version 2, Wireless USB Server Monitoring System. It's by Alan Falk, Leah Stewart, Fungyu, and Kelsey Yoshizawa.
Hello everyone, welcome to our presentation. My name is Alan Falk, and our capstone team is FireComb II, and we present a wireless USB device. So first of all, let me introduce our project manager, Maria Stewart. And for the hardware team, it's including Alan Falk and Fungyu. For the software development, we have Kelsey Yoshizawa, and our mentor is Dr. Wikimura. Our sponsoring company is Silicon Mechanics. On this slide, I will go over all the materials that we cover in this presentation. First, we have an introduction, motivation, overall system, and layout diagram of the subsystems, hardware system design and software system design. And we have a design analysis of the scalable system, conclusion, learning outcomes, and acknowledgement. Our sponsoring company, Silicon Mechanics, Fortune 5000 company, specialized in designing and building custom enterprise-grade solution for the server, storage, and high-performance computing hardware. This project was presented by Daniel Cho, the Chief Operating Officer and Chief Technology Officer of the Silicon Mechanics. The original idea of this project is to create a wireless USB device to indicate the status and location of the monitor server. For the motivation, first I go over what the previous team has done. So they did some testing and accomplishment. They were able to receive and transmit the data from the USB child device to the mother device and host server. They also able to detect the server health such as power loss and the unset temperature. They also did some demonstrate about the communication range about 30 meters. So now our capstone team will improve the goals by extend the communication range from 30 meters up to 100 meters and create a beta units for testing on a small scale and pseudo server farm. And also we have a graphic user interface that allow technician can see what's the problem of the server. Also, we upgrade the power supply of the system from 2 coil battery to the rechargeable battery. Also, we have some protection case for the child device and mother device. And we design analysis of the scalable system. So I review the function of the overall system. As the picture over here, we have the server, and this is the child device, which is plugged into the server, and it's get the data from the server and send all the data to the mother device using the XP radio wireless. So from here, the mother device will receive all the data, and it will report the problems to the host server, and the host server will direct the technician to find a specific server that has problem and need to repair. And also we upgrade the graphic user interface with all the information and the alert that technician can, that helpful for technician. For the layout diagram of the subsystem, Now we go over the child device. So the child device has the XP as a radio to transfer and receive the data from the mother device. The IC chip is the chip that allows the child device to get all the data from the server. And when there's something wrong with the server, the child device can turn on the LED to indicate the problems. The mother device is not as simple as the child device. It's a high level device, so it has a Arduino microcontroller. And the reason that we need that is to tell the child device what to do and to turn on the LED. Okay, now I will pass to Phương Vũ. She will talk about the hardware system design.
Hi everyone, my name is Phương Vũ, the hardware team member. I'm going to talk about the hardware system design part. From the phase 1 child device, the custom team built two regular coil cell batteries to power up the ISP radio to send the message to the mother device. Notice the mother device has the error power outage, and the battery also turn on the LED to help the technician identify the location of the child device for further troubleshooting. So two regular battery didn't last long, and we had to change frequently. And you imagine that you are in the in the server farm with 1,000 servers, and you cannot find a specific child device to change the battery frequently. So to solve that problem, we want to upgrade the child device, the two regular batteries to one rechargeable batteries using the lithium-ion polymer rechargeable batteries with the advantage of light and powerful. It can deliver the output of 500 milliamp per hour at 3.7 volts, and it also shrink down the size of the PCB. Besides that, we want to use the standalone linear lithium-ion battery charger with the function to charge the single cell lithium-ion batteries directly from the USB port and maximize the charge rate without the risk of overheating with the thermal regulation. To extend the chain from 30 meters to 100 meters is one of our goals. We choose the programmable version of SP Pro S3B radio. As you see here, it supports the radio frequency ideal range of 305 meters with the data rate up to 200 kilobytes per second. With the programmable version SP Pro, they have the IC, the secondary IC chip here with 32 kilobyte flash and 2 kilobyte of RAM, which is used to replace one of the AT-Tiny 85 processor from the previous child device, with the function of send the message to the mother device in case of power loss. And the ISP also requires 2.4 to 3.6 volt power supply, and it's used digit mesh networking protocol for the fast speed data transfer and the brain extension. For the enclosure, with a big tank from the member from Silicon Mechanics, the company, Britain and Justin, we are able to complete our final prototype 3D printed encasement for the child device with one open end for the USB connector and the other end for the LEDs. Here is the final complete PCB of the child device we had complete. The PCB with the half of the encasement with the battery underneath and the SB on top. And here is the PCB with the battery and without the SB on top. So you can see this, the SB radio without the SB radio. SB radio given a lot of space underneath, so it's allowing us to rearrange the components to make the PCB more compact. During the process of hardware design and testing and debugging, we faced two major problems. The first problem we have is the program, the secondary IC chip. This chip is not compatible with Arduino IDE software, and it's used the XP specific code warrior software is a new embedded software development tool. By the time, we didn't expect that the code warrior take a lot of time, and also to upload the code, we need the XP development kit. By the time we realized we really need that kit, it's too late and to purchase, and it's really expensive. Another major problem we felt is we unsuccessful to set up the XP radio communication wirelessly from the child device to the mother device. The radio, the new version of the radio, XP radios is only communicate to each other using the new version of XCTU, a multi-platform application. But it's not wirelessly, communicate wirelessly on so we have been trying the old version of the XP radios with the old version of the XCTU on the new PCB to prove that the problem is not from the PCB, but it's from the new version of the XP radios. So here is the communication result from the old XP to XP using the new PCB. So you can see here the monitor server. The child device is commanded to send a package of hash number to the XP on the mother device, and give the XCTU version, old version, and we have the XP on the mother device receive the package of hash data from the child device. But I'm going to pass to Kelsey if you see your word to talk about detail about the software.
So hi again, my name is Kelsey Yoshizawa, and I'm the software developer for this project. And I'm actually going to start with what the old GUI used to look like, because one of our main changes was updating the GUI. And so on the left here, you can see that it was pretty simple before. When it was operating normally, it had the words humming along, highlighted in green, and didn't give any other information aside from that. On the right-hand side, you can see that when there's a server fault, it then switches to saying server fault highlighted in red. And beneath that, in this small text box, indicates the XP address and the error that's occurring. However, this was only for one device at a time and didn't really give that much information. So our main goals were to improve the GUI by making new information accessible, and by also adding like color coding and sorting functionality to make looking at more information easier and identifying problems easier. And so here on the right is like a prototype of what we hope the GUI would look like initially. We also wanted to improve the check cycle to include additional information, such as temperature values, instead of just saying whether or not the temperature was too hot or cold. And so to kind of give an overview of how the entire system works, we start off with childcom.py, which is the Python script that runs on the monitored server. That is the script that initializes communication with the XP through the serial port, as well as gathering the information on the temperature using the server's own sensors. From there, it kind of sorts through all of the temperature data gathered on the core temperatures and the die temperatures and picks the highest one because we care about how hot the server is. And then uses the XB to communicate 5 bytes of information. And so in the first version of the project, all 5 bytes were used to communicate an error sequence that just indicated if a problem was present and if it was temperature or power. And so this time, I actually switched that so that the first byte of that sequence is used to indicate a flag as to if the message being sent is a power message, a temperature error, or a normal temperature. The next 2 bytes are used to transmit the information that follows it, such as the amount of time that the power has been out, or the actual temperature value that was taken from the server. So through XV, that's sent to mother error handling INO, and that is the Arduino code for the Arduino microprocessor that is the mother device. And that receives the information and interprets the first byte of whether or not it's a power or temperature message, and then proceeds from there. So if it is an error, it'll send a signal back to the XV device, telling it to set remote state, turn on the LED that will, on the child device that will indicate where the problem is, and also what information that it needs to update the GUI with, whether it be highlighting errors or updating the information, and including the timestamp of the message. So that goes over to fireserver.py, which is the Python script on the host server that takes that information and checks for either status requests or status updates. That is forwarded onto com.js, the JavaScript file that is used to update the GUI, and then over to index.html, which is the actual HTML file where the GUI is. So here are some software flowcharts of the mother error handling process, which is the procedure I just explained of the mother receiving the message and checking the flag, and then either updating and highlighting rows or just updating with new information. On the right is the new check cycle process, because so the mother has another functionality where it checks that the XVs of the child devices are still in communication, they're still functioning properly. Or else a server could go out or an XV could go out and never report a problem, and you would never know that it was out. And so it used to just check that the XV was alive and then move on to the next one. But now, because we're updating with new information, we also take the timestamp information and update the GUI before moving on to the next event. And so again, here's the improvements that were made to the GUI with the temperature values, the time elapsed, the errors, highlighting, sorting, and you'll actually see that following, which is here, the test case for the GUI, which shows power loss error highlighted in pink, high temperature errors highlighted in yellow or orange, the actual values of the temperature, and during a power loss error right here, the amount of time that power loss has been out. And then on the following slide, highlighted in red is under the circumstance that you have both a high temperature followed by a power loss error, and then you lost the power to that server. And so a few of the problems and issues that we had with software in the end included just programming on the servers was a first for the entire team, and so we had some troubles troubleshooting the entire communication system of tracking a message from getting from the host or the monitored server all the way through to the host server. Most of that was because of the XP communication issue that was brought up in the hardware section. Also, our inherited software was not functioning as intended for the mother device. So although it was reported that it was supposed to do a certain thing, it turned out that we didn't get physical copies of the software. It was just in a copy and paste into the document. And so when we tried to put it together, it wasn't functioning as it was supposed to. The hardware compatibility with the AT-Tino85 and the whole IC, not being able to program the IC chip was another issue that was covered before. And just time constraints, because by the end we ran out of time, but I feel like if we had more time to work on it, we probably could have debugged the software to make the entire thing function as proper. So now I'll pass it on to Malia Stewart, who will cover the design analysis of a scalable system.
Thank you, Kelsey. Hi everyone, my name is Malia Stewart, and I'll be discussing about the design analysis of a scalable system. So in doing this, we want to evaluate the functionality of monitoring the system on a much larger scale. And as well as in the future, there could be a potential implementation of this in a real life server farm. So not only will we be monitoring hundreds of servers, but thousands and 10,000s of servers. So given this, we also want to take the initial considerations. So they are followed as 1, we want to determine what are the maximum number of children one mother can actually monitor a number of child devices. 2, we want to look at the communication time. What's the maximum of time of communication between those two devices? And 3, the communication range of devices. What's the maximum range that it can communicate? And lastly, the dimension of the area being monitored. So given here, we have 2 different layouts. So we have one layout that shows the general layout, and it just shows like a typical hierarchy system. So you have your master mother device, as well as monitoring your sub-mother devices that are monitoring the maximum number of children. And then we also have, to be a more specific layout, we have the communication layout. So you would have one master mother, and they'll be monitoring the mother devices. And all of the children, the maximum number of children will be at an arbitrary range. So be whatever maximum communication range it will be at a distance between both the mother and the child. And also, the purpose of actually doing this was determining if there is even a need for a master device. So given with all the information, we have the first order. So the first order, it will be, for example, how many children devices can one mother monitor? So given that, we have the following parameters. We have R, the maximum communication range between the mother and the child. And we have N, number of children in the monitored area. And we also have capital N, the maximum number of children. And we also have your total time of monitoring the children, as well as your set time. So your set time will be the maximum time allowed for monitoring the children. And also given with these, we want to look at all the equations that we have. So we have the area of communication. So given here, you see over the circle here, that will be your area, the communication that the mother will be able to communicate to each child. And then you also have your density, which is the number of children per square footage in the server farm right here. And then also, you also want to determine what is your total time. So by determining your total time, you will take the number of children multiplied by an arbitrary time, so a reasonable amount of time to check each child. And then once you calculate your total time, you will then do a conditional statement if it is less than your set time, which is, as a reminder, maximum allowable time of monitoring the children. So given with that, you would then be able to determine what is your maximum number of children in this given case. And then also for your second order, instead of determining the maximum number of children per mother device, you would want to determine what is the maximum number of mother devices per master. And in doing so, you're given the same equations, however, you want to calculate a different total time. So rather than calculating your total time based on the first order, you would then use the value that you calculate from your first order, maximum number of children, and you would multiply it times the time it takes for one master to check each mother. So by given this information, you would then have your new calculated total time. And by following that with a conditional statement, comparing it with your set time, you would then do a similar process in order to get a similar goal in determining the maximum number of mothers. And then it keeps going on the higher hierarchy that you go. So, such as, for example, if you want to monitor maximum number of master servers per supermaster, you would keep following the same process. Therefore, to wrap it up, in conclusion, all of us as a team, we have accomplished goals. So the following goals that includes is making the child device as compact as possible, and that includes also creating a protection enclosure, so a 3-dimensional encasement. The following is we've improved the GUI and then also provide additional information. Next one is that we have 1 rechargeable battery, so such as from the previous team, instead of having 2 coin cell batteries, we replace that with 1 rechargeable battery. And also we've executed a design analysis of the scalable system. So what we found too, like for the next capstone team, for their next task is to actually purchase the development kit for the XP, and as well as re-implementing the power loss monitoring functionality, and lastly to improve multitasking of mother monitoring loops. And then also in addition to the next team, we also recommend the next team be mainly the software. Because it seems like for hardware, it doesn't seem that there's too much being done for hardware since we've already kind of made it as compact as possible. So mainly all of the improvements and the expansion, it can be done in software for more improvements. As far as the learning outcomes, we've learned a lot of things, the content and everything from general to detailed content and working with the capstone. And the following is, one is how to prepare components for the soldering company. It's our first time that we actually haven't hand soldered all of our components. So we had to learn how can we prepare all of the PCBs as well as the components and giving it to the soldering company. So there will be no mistakes in soldering. We've also learned how to use the CAD software to design the encasement. So for our three-dimensional encasement, we learned how to use the CAD software and preparing for silicon mechanics to design it. And also we learned how to design the PCB for fabrication. We've also learned the networking and the monitoring programming during this project, and as well as many languages, as you can see here. So ranging from Python all the way over to HTML. As far as advice goes for future capstone teams, we, just like every other capstone team, we definitely give advice to begin the designing phase as soon as possible, such as early as capstone 1. We also advise maintain constant communication, as all you know, communication is very important. So we advise them to maintain communication with all team members, advisors, sponsor, client, everyone. Also to obtain additional feedback and critique from faculty members, such as for your PCB design, if you want someone to review it, definitely have that reviewed as soon as possible. And also for any phase 2 or higher projects, definitely ensure that the inherited material functions as reported, such as like when Kelsey was mentioning about the software and all the coding. Some of it was missing, so we had to, it kind of took us back a little bit, so we had to make sure how to, you can say like, look over it again and then make sure there's no other mistakes that's been passed along. So that's definitely important. And then with that, that also brings up to perform thorough research in both hardware and software and integrating them together, and as well as completing necessary testing and interpret previous works. So given with that, we'd like to end with our acknowledgements. We want to highly thank our executive team that includes Ava Cherry, Daniel Chow, Andrew Hayda, Britton Sheen, and Justin, as well as Maximilian Gobu, especially for him since he first started the GUI work in the previous capstone team. So without that, we wouldn't have even learned how to do the GUI or anything without his support and help. As well as a supporting company that did the professional soldering for in-circuit assembly. And huge thanks for Silicon Mechanics for even giving us a chance to work with them in this project. And last but not least, our supporting staff, Dr. Wayne Kimura, as well as Dr. Arnold Berg for their constant encouragement and helping us throughout this project. Thank you.
If you lost communication with a child, how would you know what happens?
I can do that one. So right now, actually, because the XP communication didn't work, we couldn't send out power loss message, which is why in the next iteration of the team we suggested that they re-implement the power loss functionality. But that is done through the child devices having the programmable IC chip. So it detects the voltage difference from it being plugged into the server, and if that voltage is to drop, it then recognizes that as a power outage, and running off of the rechargeable battery powering itself turns on the LED and sends the message to the mother device.
So, is this software that already exists before you actually working on it, and then you just like kind of improve the performance of the software, or is this something completely new that you guys developed?
Okay, so some of it, like the basis of that was already created, such as like the original functionality of detecting if there is a high temperature problem and sending it. But we had to do a lot of work in changing a lot of the code just to be able to set the actual values and change the byte sequence. Also, the HTML was very, very simple, and so I basically had to redo that from scratch. And I used the same outline of the template, but had to change pretty much all of it.
Oh, yeah, because the reason I asked, because I see the new version of XD and the new version of the XCT. Yeah, because like, was there something you guys was trying to improve on?
So the XCTU software and the XVs are actually available for download from the company, Digi. So that's not something that we actually worked on. That was just in regards to the communication of the new XV devices not functioning as proper as it was supposed to. Because of that, we actually tested everything with the old version of the XV because it was working with the old version of XC2 that was required to test it to prove that the PCB was on what had the issue.
Okay, very good, thank you very much.